Let's take a look at example 3. Let's solve y double prime minus 6y prime plus 9y equals to t squared e to the 3t with initial conditions y of 0 is equal to 2 and y prime of 0 is equal to 17. The first thing we're going to do is we're going to begin by taking the Laplace transform of both sides. Again, knowing that the Laplace transform is linear, we can kind of skip a step and just write it like this. It's going to be the Laplace transform of y double prime minus 6 times the Laplace transform of y prime plus 9 times the Laplace transform of y, and it's going to be equal to the Laplace transform of t squared e to the 3t. We know that the Laplace transform of y double prime, that's s squared times y of s minus s times y of 0 minus y prime of 0 minus 6 times, again, be careful with your parenthesis usage here, the negative 6 is going to get multiplied by the Laplace transform of y prime. The Laplace transform of y prime is s times y of s minus y of 0 plus 9 times the Laplace transform of y, which we simply call y of s. Okay. On the right hand side, that's going to use our theorem 7.31. This thing here is simply going to be a translation. This is going to be 2 divided by s cubed typically, but because of the e to the 3t term, it gets translated, so it's going to be 2 divided by s minus 3 to the third power. And technically it's 2 factorial, but 2 factorial is the same thing as 2 because it's just 2 times 1. Okay, so far so good. We applied the Laplace transform to both sides. We now want to solve this algebraic equation for y of s. So I'm going to plug in my values that we know. Recall that y of 0 is equal to 2, and y prime is equal to 17 at 0. So we have s squared y of s minus, this is going to end up being 2 times s minus 17. I'm going to do 2 steps at once, so I'm going to distribute the negative 6. We get a negative 6s y of s, and then recall this is going to be 2. Negative 6 times negative 2 should give us positive 12 plus 9 y of s is equal to 2 divided by s minus 3 cubed. Let's try to combine some of our like terms if we can. We have an s squared y of s. There's a negative 2s. Negative 17 plus 12 will give us negative 5 minus 6s y of s plus 9 y of s. And this is still equal to 2 divided by s minus 3 cubed. I'm going to do 2 steps in once. So what I'm going to do is I'm going to get rid of all of the non-y of s terms on this side. So in order to do so, I'm going to have to add 2s plus 5, add 2s plus 5 to both sides. And now the other thing that we're going to do is let's kind of go ahead here and factor out the common y of s term from the left-hand side. We'd have an s squared minus 6s plus 9. That is times y of s. And this is going to be equal to 2 divided by s minus 3 cubed plus 2s plus 5. And then if we notice, just looking at this thing here, we're going to divide both sides by this factor, but notice this is actually a perfect square. This would factor which you could do now or you could do in the next step. But this is simply s minus 3 squared. Y of s is equal to 2 divided by s minus 3 cubed plus 2s plus 5 as it is. So we're now going to be able to get y of s by itself. Let's divide both sides by s minus 3 squared. Divide by s minus 3 squared. So essentially every term is getting divided by that s minus 3 squared. And this gives us our y of s. So here's where we're at. We have that y of s is equal to, if we look at this thing here, this is going to be simply 2 divided by s minus 3 to the 5th plus 2s plus 5 divided by s minus 3 squared. And now our very next step is we've first of all taken the Laplace transform of both sides. That gave us an algebraic expression for y of s. We have found y of s, we got y of s by itself, and so now we can find our solution. Our solution, y of t, is going to be found by simply doing the inverse Laplace transform of y of s. So we need to do the inverse Laplace transform of 2 divided by s minus 3 to the 5th plus 2s plus 5, all divided by s minus 3 squared. And for this one, we can kind of cheat a little bit. This one's perfectly fine. This one's already kind of set up to go ahead and do immediately. But you might recall this expression might look familiar. If we go back and look at the result, so we did this in example 2 part A. Typically you would have to do partial fractions decomposition with something like this. But this thing actually breaks apart. This is equal to 2 divided by s minus 3 plus 11 divided by s minus 3 squared. So that saves us from having to do an additional partial fraction because we already kind of did that one before. So here's where we're at. This is going to be the inverse Laplace transform of 2 divided by s minus 3 to the 5th plus 2 divided by s minus 3 plus 11 divided by s minus 3 squared. Again, the inverse Laplace transform is linear, so we can go ahead and split this apart. This is equal to 2 times the inverse Laplace transform of 1 divided by s minus 3 to the 5th plus 2 times the inverse Laplace transform of 1 divided by s minus 3 plus 11 times the inverse Laplace transform of 1 divided by s minus 3 squared. So let's kind of go ahead and break these things apart. So for this one right here, again, this is going to be a shift. If we look at this, we can rewrite this as the inverse Laplace of 1 divided by s to the 5th, with the shift s going to s minus 3. This one here is in a direct consequence. We know that this one's going to be immediately 2e to the 3t. One of our basic rules. And then this last one is also a shift. This is 11. This is going to be the inverse Laplace transform of 1 over s squared, where s is getting shifted to s minus 3. So we're almost there. So y of t is going to be equal to, now for this one right here, recall that if we have an exponent of 5, to do that inverse Laplace transform, we would need to have a 1 less than that factorial up top. So I would need a 4 factorial up top, which means I would have to divide by a 4 factorial on the outside. And then if we do that, this is going to give us a 2 over 4 factorial, the inverse Laplace transform of s to the 5th power, that's going to be equal to t to the 4th. But because we have the shift there, s to s minus 3 provides an e to the 3t term with it. Plus, then the next one is our 2e to the 3t. And then plus, again, if this is 2, you need a 1 up top, 1 factorial, but that's already 1. So this is going to be a basic shift operator. The inverse Laplace transform of 1 over s squared would be t, but we have the shift s going to s minus 3 is going to provide an e to the 3t out in front. And so there's our answer. Only other thing we can do is simplify the factorial part of it. 4 factorial is 24. 2 divided by 24 would provide us with 1/12. So the solution is 1/12 e to the 3t times t to the 4th plus 2 e to the 3t plus 11 e to the 3t times t.